For those who do not know me, I'm François Maréchal. I'm professor here in UPFL, Mechanical Engineering Section and Institute. I have my office located in Sion, in Valais, and I'm leading a research group there which deals with process and energy systems engineering, and so we are around 30 persons working there. So for those who are interested, there is also the possibility of doing semester project or master project with us. One of the topics that we are dealing with is the modeling and the optimization of the energy systems. So I will be helped in this course, so you will be a lot, so officially 75 persons. There will be also, so I will stream the course, so if everything works then you can follow the course in the other room as well. And I will be helped by the assistants who are here today. So Alessio, who will be the coordinator of the assistant, and on the back you have John TV, we name it TV, so Tristan and Red. He's a postdoc in my group, Julia and Xiang, who are PhD in my group, so you can just raise your hand so that you can identify yourself. And I guess that Luis will also, and Rafael will also be helping us. The reason why we need so many assistants is that we are going to work together. It's not only a question of me being streamed on the video, but it will be more you learning things about how to make use computers in order to design and make and operate in an optimal way energy systems. So what does it mean? It means that we first have to realize that we have to look at a system, and a system is typically a piece of land in which we have to supply services. So, and the piece of land is located in a given place. It has a socio-ecological economic context. It means that the people have to accept the rules of the place where they are located, being the economical or the wish of the people, and the environment that is imposed. So, for example, if I'm working here in Lausanne, I will see that, oops, I have a lake, so I can perhaps use the lake, right? And the people are asking services, and services are, so that's what I'm naming the energy services, are related to the fact that the people would like to be comfortable. So, for example, you are in the room here and someone is taking care about heating the room. This one has no ventilation, I can see, but some of them are ventilated, so that they try to control the air quality as well. But the fact is that when you ask something, you have to look at variations with time, and there are a lot of technical systems that are used in order to satisfy your needs. So, for example, being here in this room to attend a lecture, or being in a workshop to produce products. Okay, so those are the services that the people need, and they are ready to pay for those services, and we have to supply them with the services, and we are going to use resources to supply those services. So the resources can be the one that we have here. So, for example, the heat that is in the lake, the sun that is shining, right? All the water that is flowing in the river. Or we can use resources that we have that have been harvested somewhere else. So, for example, I can use the gasoline that is in my car, which has been extracted in Russia, for example, that has been transformed, distributed, and come here at a given price in the filling station. So what we can see with this is that the energy that we buy is coming at a given price, which will differ from the seasons. So in winter or the summer we will have different prices, and or different availability. So for example, the sun is not available during the night, so we have to take this into account when we will have to design the system. And the system, what is the system? Is a set of equipments that is going to take the resources and that is going to make the products and the services that are needed by the society. And the role of the engineer is to try to make something which is efficient. Efficient in the sense that the maximum amount of the resources that is used in the system needs to end up into something which is useful. And this is because the first principle of thermodynamics is telling us that everything that is not used for something that is useful is wasted and released in the environment. Okay? Or needs to be treated in order to be released in the environment. Right? So it means that the goal of engineers is to try to make this, to maximize the efficiency. And I have added another important role here is the recycling. The recycling that is telling us that sometimes a waste or a depleted products can become a resource. So for example, the waste of your food usage is ending up in the waste treatment plant, in the wastewater treatment plant, and the biomass that remains in the wastewater can be converted into methane that can then be used as an energy resource to produce electricity. Right? So it means that we have to account for this recycling element here. So as soon as we do a conversion, then we know that we will have an impact. And it means that it will have an impact on the environment. And that the people there will value the quality of their environment by setting up rules or conditions on what is allowed to be released in the environment. So for example, in Switzerland, it is not allowed to directly landfill the waste. So the waste is collected, is treated, okay? And the amount of waste that is sent to the landfill is much lower than in other countries. And this is a rule that is imposed by citizens that are living in this environment. So what is the role of the engineers there? So the role of the engineers is to design the system. So now I'm not talking anymore about this very nice set of flows. I'm talking about equipments. So the engineers have to design the equipments that allows to make the conversion from the raw materials to the end products that are needed by the society. So now if I'm looking at in the details, what does it mean? It means that I have to choose the type of equipment that I'm going to activate. Do I use a boiler or heat pump for heating a house? I'm going to define the size, so what is the size of the boiler or what is the size of the cogeneration engine that I'm going to use. I'm going to also define how the equipments will be interconnected. An example is that I have waste, I can decide to burn the waste, and I have to use the waste heat of the burning process in order to produce heat for the city. I will therefore have to install heat exchangers and pipes that connect heat exchangers. But I can also buy a steam turbine that is going to use the high quality heat in order to produce high pressure steam, to produce mechanical power that will be connected into the electrical grid, and use the waste heat to heat the city when the city needs to be heated, which means that most probably I will have to also to buy another equipment. There will be a condenser that will be used when nobody needs the heat to release the heat in the environment. Okay, so it means that I will have to buy equipment and I will have to make interconnections between those equipments. And then I will have to define the strategy with which I'm going to operate the different equipment. So at which temperature I'm operating a heat exchanger, at which pressure I'm operating a compressor and a heat pump. Okay, I will have to define all those elements, and we know that the demand is varying. So it means that I will have to use a specific method to define what is the optimal operating conditions for those equipment. So the engineers have to decide what, when, and where. Okay, and this is the difficulty of the engineering work. Okay, at the end you will have to buy the equipment and you have to give a proof to the stakeholders, so the people who give you the money, that the design makes sense. Okay, and that they will earn money with the system that you have installed. So now what we are doing in my group is to try to develop the methods that allows you to go from I would like to heat people, or I would like to that the people are comfortable, and I will do it in this way, which is the solutions at the end. And typically we go through a list of steps. So the first step is, what is the system boundary that I'm going to, what are my goals, sorry, what are the resources that I have, and what is the context in which we are going to work. Second step is to define what is the system boundary. So when I'm, for example, deciding to heat or to supply the comfort in the site of the PFL, I have to decide if I'm dealing with this building, or if I'm dealing with all the buildings, or if I'm making a deal with the UNIL in order to heat also the buildings of UNIL. Okay, so I have to define the system boundaries. Then I will have to define the technological options. And as I'm creative, I will have a lot of options in my mind. Okay? So if I tell you how do you heat a building, how would you heat a building? If you had to decide to heat a building.
Geothermal.
Geothermal with heat pump. Okay? And you?
I would not say heat pump, but the air.
So heat pump with the air. Yeah? Yeah, say it. A solar system, yeah.
With hot water from industrial pump.
So with heat recovery.
Yes.
The gas used in?
Turbine.
In a turbine?
Gasoline,
And in gasoline, and where do you use the gasoline?
either on a burner or maybe a turbine.
A boiler, a turbine is, yeah.
Same principle with biomass.
So biomass, so what you can see is that, so I have only taken the two first rows, and I have already 10 options, right? You could have added fuel cells, you could have added cogeneration engines, okay? So it means that you are creative. And in fact, I did not ask which refrigerant was used in the heat pump that they were proposing, right? So it means that engineers can be creative, and then you can say, okay, but especially if you are using solar, that, yeah, so the sun is not shining a lot in the fall, for example, here, okay, because there is a lot of stratus. So perhaps we have to combine systems, okay? So if I'm buying PV panels, then I need something that is going to make the battery. Okay? So, conclusions is that engineers are creative. And if they are not able to compare all the solutions, they will be frustrated. Okay? And for this reason, in fact, you need models. Models that will give you the impact of the decisions you will take. Okay? And in order to be able to model the combination of different solutions that we can imagine here, we have to have systems that allow us to generate in a systematic way interconnections. Okay, so we have to connect. And perhaps that I will use a heat pump to preheat and a cogeneration engine to finish the heating. And I will use the electricity from the cogeneration engine to drive the heat pump, right? That will be fed by the geothermal, except that I can also use the wastewater, the heat of the wastewater treatment plant that is just there. Okay? So I will have to make the interconnections. Then I have to ask myself, is it enough to just make the simulation? That means I have a lot of options, but now you have to tell me what is the size of the heat pump, and you have to tell me what is the size of the boiler. And then you will be frustrated because you do not know how to take decisions. So what we are going to do now is to ask computers to take the decisions instead of us. Okay? So this is what we name the optimization part. And the optimization, we are going to use computers to generate the good solutions, or more or less eliminate the ones that are not good. Right? But now, as we ask a computer to solve problems, if you just let the computer, especially if you let Bill Gates decide, okay, then you will realize that most of the time the solutions do not make sense. Okay? Especially when you ask a system to find the optimum solution, because the optimal solution is a solution that goes on the bounds, on the limit of the technologies. I'm using the maximum of the cheapest one. Okay? And so what is going to happen there is that we have to be able to understand what is behind the numerical solution that has been generated by a computer in order to convert the solution into decision. So we have to be able to understand what is the content of the solution. And most of the time when we do this, then we realize that something was missing. I did not realize that the PV panel could also be used to produce heat. Okay, and I could perhaps add a solution which is hybrid PV and thermal panels. Okay, and of course, if you end up with the analysis and say, okay, I just forget something from the beginning, I would be really disappointed. Okay, so consequence is that if you are using computers, then it's really easy to add an option and ask the system to redo the calculation and see what is the best at the end. Okay, and when I'm saying what is the best, is what is the definition of the best? The best is the solution that I'm able to defend in front of my stakeholders. So the one who are going to give me the money will ask me to defend the solution. Okay? And what I will have gained by solving this problem in a systematic way using the computers is that I will have all the arguments to defend my options. And I will have made tests to be sure that I'm at the optimal place. And I know why it is optimum. So it's not only, it's the optimum, but I know why. Okay? I know what are the trade-offs that have been generated. And at the end, by this process, then we will converge towards the best solution. Okay? And my goal in this course is that you will learn how to do it from the definition of what is the problem to be solved up to the results, which is the proposal of the last solution set is the recommendation from engineers. So, what does it mean? What does it mean in terms of energy systems, and what are the types of problems that we can solve? I can start with a very simple problem. So it's optimizing a fuel cell which is combined with a gas turbine, for example. So it appears to be a simple system. So 2 kilowatt systems, very small, but already with chemical reactions here, electrochemical reactions here, a chemical reaction here, compressors, turbines, heat exchangers in the system, another chemical reactor here. So the question is, what is the best design of this, the best configuration? So what is the size of each of the heat exchangers? What is the size of the compressor? What is the size of the turbine? So what you will realize when you have to do this kind of solve this kind of problem is that you have to go back to your lecture in turbines, okay? And then you have to look in the lecture of fuel cells, okay? And heat exchange, okay? But what we can see is that, well, when you do this job in a right way, then you can have very efficient systems. And I'll give you just one example. So we took the starting point, this problem. We analyze, we have done the optimization, analyze the results, and then realize that it would be perhaps better to not use the gas turbine around the fuel cell, like it was here, but to use it afterwards. So we just place the gas turbine afterwards. And the consequence is that this system has an efficiency of 80%. So it's much better than whatever combined cycle that is available on the market today. And it is separating carbon dioxide. So this is just the story of one study we have made. Okay? The consequence is that we have a new design with some characteristics. For example, we are separating carbon dioxide, and we were able to fill a patent. Okay, so now we have the ownership of a new system that can then be a breakthrough technology for the future. So this is one example, and this is really a breakthrough because I will replace one big combined cycle, which is the state of the art of the technologies today. By the way, the world record is 63 now, and the guy who did the calculation did use the methods, was one of my PhD students, so he did use the methods that we were developing. Okay, and he has optimized and they won so it's GE, and they have 63% today. But the breakthrough is that now the system that I was designing is a much smaller one that can be used in cogeneration, and that will replace a big unit by a collection of small units. Okay? Perhaps the challenge now is to build the factory that is going to produce all those small units. Okay? And the second dimension is that I will have to integrate this system, and why not use it with a heat pump? Okay, so now I'm going to use the electricity produced with a heat pump. So now I have my fuel cell here, the fuel cell that is going to produce the electricity that I need for, I can also use an electrical car. Now I have very efficient electricity produced, right? I will also use electricity to drive the heat pump, to supply the electricity to the people. And okay, we reach 65% of savings. Okay, so not so bad, huh? If we are looking at if you are looking at the carbon dioxide emissions. So who was in the street for the climate 2 weeks ago? They were all in exams. Huh? So let's assume that you would not have had an exam. So who would be there? So raise your hand if you are for the climate actions. Okay, so wait a moment, I'm going to take a picture. Let's do it, and I'm going to tweet so that everyone knows that we are... So wait. Okay, now you can raise your hand if you are for the climate. Okay, so you have raised your hand. So you have to know that talking about climate, the last IPCC report had said that in 2050, the world has to get rid of carbon dioxide emissions from fossil resources. Okay? 0. 2050, so it means that we have already burned 80% of the carbon dioxide that we were allowed to burn, or 80% of the fossil resources that we were allowed to burn. Okay? Now we have a window of 30 years. Okay? And what will be the age of your retreat? If nothing changed. So what will be the year of your retreat? 2000? So 60. So when will you have the age of 65? Most of you are 95, I would say. So 2060. So it means that you have raised your hand because this will be your duty. Okay? We have to reach a goal in 2050. So it means that most of you, if you are interested in energy, will be involved in this transition. Okay? This will be a responsibility for you. Okay? So I'm happy that you have raised your hand. And I'm showing you that there are solutions. Okay? I'm still using natural gas there, but okay. It's not a problem because we can also design systems that convert renewable energy resources into natural gas. Okay? And what you can see here, okay, it's a list of technologies. Okay? You have a list of options, right? So each has to be sized, and all the elements are interconnected. Okay? So the same message. Okay? You have to design, it will be not a small unit which is using, that is a small fuel cell that you can put in your car or in your basement. It will be a big process. Okay? And in reality, this big process will be included into a very big process. So the one that I have shown you is this one here. Okay? And the system that I'm showing you here is a system that is using the sun as a resource, and that is supplying fuel for the fuel applications, that is supplying heat for the district, and that is managing the energy. So you can see that I have again interconnected subsystems by pipes, by an infrastructure which is a well-known infrastructure with tubes that transport heat, that transport gas, that transport electricity, okay, or that transport wood, or waste, or carbon dioxide. Okay? The technology of the pipes is known. Okay? The technology of a heat pump is known. The technology of a fuel cell is known. So what you have to do is to make the right assembly of all these elements here. And you can see that there are options, so there is not a single option. Something which is also important is that we are going to integrate the sun, so it means that we have to look at the variations of the sun. Okay? And we have to be able to cope with the difficulty of recognizing that, for example, when I have to heat a building, the sun is perhaps not shining. Okay? But I can also realize that I have options that works. So, for example, I can use the electricity that is produced by the PV panels, okay, to drive a heat pump that is going to produce hot water that I will use when the sun is not shining anymore. Okay? Now the question is, what is the best size of the heating tanks here? And when do I operate everything? Because, of course, I will not have to use the electricity in the heat pump if I know that I will not be at home. Because then I can sell it to my neighbors. Right? So it means that I will have to integrate in the design the fact that I know what is going to happen, and then afterwards I will have also to install a system that is going to operate in a proactive way, knowing when the people will be there to prepare what they need. Okay? And we have also to recognize that there are smart people or smart companies around. So for example, Google is selling you a thermostat. You have already seen the thermostat of Nest, the Nest thermostat from Google? No? It's a very nice system that you have on the roof here, on the wall, okay? When the temperature is too high, you decrease the temperature. When the temperature is too low, you turn on the right and you increase the temperature. So a big revolution. You pay 500 Swiss francs for having this kind of device. And it's a very big revolution. Yeah, you agree. The revolution is behind, okay? Because of course you do not like to go to the wall to change. So they offer you to do it on your iPhone or smartphone. Okay, so now you can have your phone and you feel hot, you decrease, and you feel cold, you increase. Okay, and you show this to your friends, and you are really proud of having this working, and effectively it works. After 3 weeks, it appears that you never touch these apps anymore. But each time you enter in the room, the temperature is the right one. Because the system has learned your behavior. Okay? And the system knows where you are. Okay? So it means that now I have a system that is able to predict when you will be there and what will be the temperature of your comfort, and advertise and sell the information to the electrical company that knows that you are using a heat pump and that is going to tell you, okay, at this time I will offer you a special price of electricity because I do not have users and I have too much on my solar panels. Okay? And of course, the condition is that you have to have the heat pump and the right storage tank or the right battery. Okay? So now that means that you have to integrate also the operation in the system. And then there are other systems that can also be solved. So let's imagine a car or a ship. Okay? Difficulty of a car or a ship is that the demands are always varying because you have to accelerate and brake. Okay, you have to be sure that you have enough energy in your tank. Okay, to go from the point A to the point B that you need. So the services that is needed by the car. Okay, and you have to set up a system that is a combination of perhaps an engine or a fuel cell plus batteries plus electrical engines. Most of the future cars will be electrified. Okay, so to supply the services, and the services is not only the mobility, but the comfort that you need inside inside your car, or even the safety management, or even the scheduling part. Okay, so it means that you have a system that needs to have that is disconnected from the grid. So it means that for a certain time it is an autonomous system, okay, that needs to have enough fuel in the car, and I guess that in the future you will be happy on not having to decide to fill the car with fuel, but when you will take the car, it will have the fuel that you will need for doing the next travel. And it will be the same for the same approach is for the airplanes or for the ships. Okay, autonomous systems. But again, the question is, what is the best size of the different equipment in the system? What is the strategy of operation? What do I do when I'm braking? What do I do when I need to accelerate? Okay, and what are the different sizes of the different systems at the end? Because I want to propose this product on the market. Okay, so this is another type of system, and then the other one is the city. So the other one is the city in which you have the possibility of sharing of equipments or resources. Okay, so for example, you can have a system that is going to harvest heat when you have waste heat, that is going to deliver heat at the temperature that is needed by using a heat pump, that is going to take the heat from the geothermal, for example, at the right place. So not necessarily here, if something is, if I have hot water available at 10 kilometers from here, okay? I will have to design the pipes that connects the different buildings, and I will have to design the system that is going to make the energy management, okay? So I can have a lot of small fuel cells everywhere that can be activated when I need electricity, and it will be activated because I know that I will use the waste heat for heating buildings, okay? With the corresponding sizes of the different tanks. Okay, so it means that now I show you that the problem can become very complex because we will have to look at all the buildings that are in a city, okay? And I will have to manage the whole system, looking at the time where, and this will be something which will become very important in the future, the time where I will have electricity available. So that means electricity that nobody needs. And I will have too much electricity, I can tell you, because of all the PV panels that will produce a lot of electricity in the winter, in the summer, sorry. And you will need the electricity in the winter, so it means that you will have to have energy management systems that is going to store the electricity that you have in excess in the summer and send it back in the winter when you need heat. Okay, so all those elements are the seasonal storage equipments that will play, will come with in complement from to the batteries, and all those equipments interconnected one with the other will compete one with the other. I will not install a chemical storage, for example, in form of hydrogen, if I can use the excess of electricity in a pump hydro system. Okay, because the pump hydro system, if it is there, will be cheaper and more efficient than a hydrogen storage. But at a certain time, all the dams will be full, and then the last part will need to be taken by hydrogen. And you have to know what is the amount, because you have to know what is the market and when the electricity will be cheap. And this then brings me to the last dimension, which is the circular economy. So it's to realize that the needs from the energy system is not only from the people, sorry, it's not only energy. So they ask you also to do the waste management. Okay? And the waste that the people produce needs to be treated. And the best way to treat the waste is to recycle. Okay? Or to reuse first, and then to recycle. And then after to convert into perhaps waste energy that can be used to heat buildings at the time when the buildings needs to be heated. And at the same time, I will have to realize that it's not only the people, okay? It's the whole industry that has waste. Okay? That's the whole industry that can recycle. So perhaps we can recycle solvent to produce cement. Okay? So it means that I will have to understand the whole system integration and propose the final solution. So I hope that by this I have convinced you that understanding the system is very important. The number of options is very, very high. And the design of the system means not only to look at what is the size of the heat pump that I have to put in the building, but it's the size of all the equipments that I will have to put in the system, including all the ones that allow to create a dephasing, a storage, short-term and long-term, that needs to be interconnected, so the size of all the interconnecting pipes, okay, in such a way that they satisfy the needs of the people with a maximum profit. And the maximum profit will be the difference between how much you have invested, how much you spend to operate it, and how much you receive from the people that are ready to pay for a given service. Okay? So let's now, this will be really my conclusion. There is a need to have a method to design those systems. Okay? So I'm going to make a break, and then afterwards I will show you how we will do it. So, let's start again. I will give the answers about the organization of the course in 3 minutes. Okay. I just want to highlight what is the meaning of modeling and optimization of energy systems by just showing you what it means when we have to design a simple system, like a combined cycle that is producing electricity out of natural gas. So the first thing you need to know is to have the thermodynamic models. So the thermodynamic models will be designed based on a list of units that is going to convert energy in different forms. You know the principle of thermodynamics. So for example, you have the TS diagram here of a gas turbine. Okay? You know that you have to compress, this is the first process unit, you have to burn, increase the temperature, this is the second process unit, and then you have to expand in the turbine, this is the third process unit. So you know, when you know this, then you will be able to activate, to know what are the states that are between the process units, which is the flow of energy that links and the mass and energy that links the different process units together. So you will have to know what is the amount of the mass flow, the temperature, the pressure, the composition of each of those flows. Once you know all the flows, what you will be able to do is to size the units. So most of you have, for example, had a course on heat transfer that is giving you a lot of very nice, well-designed formula that allows you to know what is the heat transfer coefficient when the flow is going to have this speed, this pressure, and this temperature. Okay? With this, you will be able to calculate what is the area of the heat exchange. With this, you will be able to calculate the size of the tubes. Okay? And the size has an impact on the flow and has an impact on the heat transfer coefficient. Okay? But nevertheless, by applying all what you have learned, you will be able to define what is the size and the shape of each of the process units. Okay? Knowing the size, the shape of each of the process units, if you know the materials, then there are some rules that allows you to estimate how much it will cost to produce all those units. Okay? So it means that now you will know what is the investment that is related to each one of the process units that you have in the system. So it means that now you know the thermodynamic state, you know the size of the equipment, and you have an estimation of what will be the investment. And then you will be able then to calculate how much it will cost to buy all those equipments per year. Okay? And then you will also be able to know, if you know as you know the flows, how much you will have to pay to operate the units, which will allow you, for example, to calculate what will be the levelized cost of the producing electricity with this system here, obtaining the efficiency, obtaining the operating cost, including the flows of carbon dioxide that will then be a tax that will be applied to the system. So doing the integral, you will know how much it costs per year compared to the capital cost that you have, and then you know how much it will cost to produce the electricity. Okay. Now, what is inherent to all the good engineers is that there is more than one option. And when there is more than one option, it means that we have to compare all the options. So I can choose different sizes, I can change the interconnections in which the system is organized, and therefore we'll have a system that is becoming more and more complex. So what I'm going to do now is to use the model that is finally using something that we name the decision variables. So those are the values that needs to be fixed so that the model is able to calculate the total cost and the emissions and the efficiency. Okay? And now the question for the engineers is what are the best value of the decision variables? So what are the flows that needs to be fixed? What are the selection of the equipments and which type of equipments? And for doing this, then we are going to use an objective function that is, for example, I would like to minimize the total cost. And I'm going to use a mathematical engine that is going to give us what is the best value of the decision variables that I have here in such a way that my objective is a minimum or a maximum. Okay? And by doing this, then I will be able to take the best decision. You have decided what is your objective function. You have defined what are the decision variables that you ask the computer to help you to find. Okay, and you have a mathematical engine here that is looking at the objective that you have, and that is going to send you the best decisions to be taken. Okay, this is the mechanism of the optimization. What I have shown you is that this is done by steps. So it's not a single step. I need to develop models. I need to integrate the options, and I need to set up the optimization problem. Something which is then also very important to realize is that we ask a computer that has no soul and that has no knowledge, that has only the knowledge that you put in. Okay, you have to learn how to use those models. Okay. It may end in what I will show you is that there are three major steps. You always have first to analyze what is the problem to be solved. Decide what is the objective function. Decide what are the decision variables. Decide what is the level of detail. Of course, I will not calculate the number of the size of the pipes before knowing that I need a heat exchanger. Okay? So I have to decide the size, the level of detail. I will also, at this stage, define what are the expected results. So I would like to know the efficiency of the system, or I would like to know how much it will cost this system. Okay? And sometimes this is also, what is very important then is that I will have to define what are the key performance indicators that I will look when I will analyze evaluate the results. Okay? So define all the elements that needs to be calculated at the end. Okay? Plus something which is important in our case is the expected order of magnitude. So I guess that I will have to buy a heat pump of 10 kilowatt and not 5 megawatt. Okay? Just to be sure that I have the key elements that are well stated. Then I will go to the next phase. And the next phase is ask from the problem formulation, ask a computer to give us numbers. Okay? This is what we name the generation step. At this step, the computer is going to crunch numbers. It is going to crunch your numbers. Okay? So it means that it is not going to crunch the numbers of others. It's your numbers with your models, so the list of equations that you have asked the computer to solve. And the computer is going to, by crunching those numbers with your models and your input parameters, is going to generate numerical results. Okay? So it means, and we have a principle that says garbage in, garbage out, so it means that if your model is wrong, and if the parameters are not the right one, the numbers that will be generated will not be the good one. Okay? So this is the generation step. So the model needs to be activated. They have to, it has to make the calculations, and you will have to learn how to state those problems. And then the next step will be to take the numbers and transform the numbers into decisions for engineers. So it means that the 373.156611992, normally it's a 216, huh? That's the precision level of a computer, right? Has to be transformed into 100 degrees C. Okay, which is something that you can then verify if it makes sense or not. Okay, so transform the numbers into engineering decisions. And you will do it by several times. So it's an iterative process, and typically it's not by pushing the button that you have the solution. So you have to push the right button, that's the one that you ask. You have to be sure that the system is making the calculations without errors. And you have to interpret the results that you obtain. And of course, if you know what you expect, then the decisions will be the one that you will be comfortable with. Okay? So, this is my goal. Those are my goals for this lecture. So at the end of the course, I would like you to be able to develop the simulation model, understand where are your decision variables, so what needs to be decided, okay? To know what is the level of detail that you will get out of the model that you are going to activate, and we will see that there are different levels of details that can be used in the system. And I would like you to be able to choose the solving methods that you will have to apply. Okay. The next step will be to state the problem as an optimization problem. So it means that then you will have to be able to calculate objective functions, key performance indicators, to state the problem in form of an optimization problem, which means define the decision variables, and choose the right method to solve the optimization problem. And depending on the type of problems, then you can activate different types of optimization methods. And then once you will be able to state optimization problem, then I would like you to apply the optimization problems and solve real problems from the energy systems optimization. So it means that you will have to state the problem, so the analysis part, you will have to collect the data, so give the right values to the computer to activate all what you have learned before and to evaluate the results and present them. Okay, so for example, you will have to be able to draw a curve that says that if I'm investing more, I will save more. Okay? So these are my goals, so I hope that you will be able at the end of the course to do all those things. Which means that now those are the elements that you will do. And perhaps I will not go into the details because it will not be clear now. I would like, however, to tell you what we are going to do together. So my strategy to allow you to be able to state problems is the following, is that you are going to do a case study. And it's a real one because EPFL has decided to develop or to renew the heating system of EPFL. Okay? And I would like you to design and propose options for renewing the heating system of EPFL. Okay? Before presenting the EPFL project, I must admit that our president, so Martin Vetterli, has asked all the professors from EPFL to make suggestions already. And this is a result of a brainstorming. So there are a lot of professors that have said, okay, you have to refurbish buildings, okay, which makes sense. The professor from heat exchangers say, okay, why don't you use the heat from data centers and use my cooling system instead, because I have invented a new one that is using refrigerant instead of hot air to cool the data center, and therefore we could perhaps use this heat to heat the buildings. There is a professor in turbo machinery that has said, okay, but it would be better to transform the compressors that we have here, which are already old, into two-stage compressors. Okay. Of course, the people from Neuchâtel have said, okay, you have to use PV panels, so cover everything with PV panels, right? And it makes sense because I can use the electricity produced by the PV panels to drive the heat pump. And my colleague, Jan Van Elmen, has said, okay, but why don't we use also a fuel cell? It would make sense as well because I can use perhaps the biogas. This was a suggestion from the people from the bioengineering that says, okay, why don't we use the biogas that is produced by all the waste that we have in the district here, organic waste we have in the district, in order to produce biomethane that can be used in a fuel cell, in order to produce electricity that will be used in the two-stage heat pumps that is heating EPFL, knowing that at the same time I'm going to cover the heat for the data centers and that I will use the electricity of the PV panels because I can store the biomethane. Okay? And So it was already nice, but then the professor of geoengineering has said, okay, but why don't we go deep? And they have a very nice technology that allows to first use geostructures and then afterwards to use geothermal heat. Okay, the professor of water treatment said, "Oh, yeah, we do not have far from here. There is a wastewater treatment plant." Okay, so instead of using the water of the lake to heat the EPFL, that is at 7 degrees C, I can use the water from the waste treatment plant that is leaving the waste treatment plant before releasing it in the Lemon Lake. I can use this water that is at 20 or let's say 16 degrees C to as a heat source for the heat pump. So the heat pump will be better, so you will need less bioethane, and perhaps the PV panel will be better used. Okay? Of course, I have said, okay, you have to do the system integration. This is me. Paolone, the Professor Paolone, who is the professor in power system, says, hey, I have a very nice big battery. Okay? So you have to use this battery because it allows me to store the electricity that is produced by the PV panel at noon in order to heat the auditorium when the people are attending lectures at 7 o'clock in the evening. Okay. You are all attending lectures at 7 o'clock in the evening, but nevertheless, so this is the future because we do not have a lot of room, so we have to maximize the use of the space. Huh? So, but nevertheless, so I have this battery, and then the people from climate, they are really interested in climate change, said, okay, and you have to be sure that if you buy electricity, it is produced from an energy, a renewable energy source, and that you have to mitigate the climate change. So please be sure that you are not using a refrigerant in a heat pump that is, has a high level of global warming potential. And then, okay, there is also a vice president who is responsible for the finance and infrastructure. And say, okay, stop. I do not have an infinite budget, so we have to do it in a smart way. Okay? And something which is also very important is that at the same time, the ETH board, which is the boss of Martin Attorney, has said, okay, but you know, we are part of the Swiss Confederation, and if the Swiss Confederation is not showing the way, then the private sector will not follow. That means that we have to demonstrate that we are the best one, especially from our sustainability dimension. So those are all the options that have been set in order to state the problem. And so what you will have to do is to propose the solutions. Okay? Among all the options, which are the best one? How much does it cost? How much will it cost to operate? Can I operate in the optimal way? Okay? And the idea would be then to say, let's generate a list of options and present those options. Okay? Before going into the mind map, I'm going to just then tell you how we will be really doing things together. In fact, I have done something which is smart. So I have asked to start at 10 o'clock, and I have reserved 2 rooms, this one and the one on the other side, for you. And I will use the 2 rooms. First, I'm going to teach you methods, and then you are going to apply the methods. The reality is that we have 5 hours together. And the other reality is that when you are in front of me, you are always saying, as soon as I'm looking at the student, it's always like this. So this will be what you will do for 2 first hours, and then afterwards you will have 3 hours, including the lunch break. And we can, if you want, we can also organize lunch together. Because afterwards you will have to work together in groups, and you will work together. We will work together on tasks that will be synthesized by the assistant. So it means that you are not going to work as competing teams, but in synergetic teams. So it means that I will ask a first group to solve 10 buildings there, another one is going to solve 10 other buildings. Okay? Someone is going to test an option, and then another one is going to test another, to prepare another option, and then we will put everything together. Okay? So it means that at the end, you will have the same system model, which will be built with the contributions of everyone here. Okay? And the assistant will take care about this coordination, so they will be sure that you deliver the numbers at the right time, and this will be then a commitment from you, because you will have to work in phase with the others, right? And we will always consolidate the data so that there is no deviation. Okay, we will at the end up with one single model that everyone is going to use to present his own preferences, I would say. So it means that you will work in groups, you will have a preferred assistant, but they will be here and they will help you. And then you will have to exchange information among the groups, and this will be done by making short presentations in which you will have to present what you have done, and open the discussions to see if the results you have generated will be or not integrated into for doing the next steps. Okay, so this will be the way it will be realized, and so you will learn as well which are the transversal skills that you need to acquire. You will have to learn to work in groups, and you will have also to learn how to communicate information among among you and with the others. Okay. From the organization point of view, so the lecture notes are available on Moodle. So the one, normally you are automatically registered. If you have problems, you ask Alessio to collect. All the other instructions are given on Moodle. You will have the PDF of my presentations, plus lecture notes, plus videos, and this year the course is streamed, so you can see me on the video already now, and then you can connect on YouTube if you want to see my face later on in the day. So it means also that if you miss a lecture, you can review the video, and some people are even learning by using the video, so you can always accelerate for the parts that are not interesting, and rewind for the part that where it is not clear. I will also open a speaker room in which you can ask questions, and that the assistant and myself will see, and we will answer those questions. So if things are not clear, do not hesitate to ask us to be more clear. And I'm giving you also some support materials. So for example, we have on our website instructions on how to write a report. I'm not going to make a lecture on how to write a report, but you can read the text. And there are also some books of reference that you can also consult. The exam will be an oral exam. You will have 20 minutes to prepare, to present your exam. In fact, you will have 3 minutes to give me a summary which is in the report that you have written on the case study that we have made together. 3 minutes to explain what were the principles or the steps that you have followed, and what were the methods that were used. And then the last 17 minutes, the next 17 minutes, will be a list of questions about the theory that you have applied to solve the problem. Okay? I will not question you about the value of a specific number. Okay? I will ask you how you have done things. Okay, and typically you will find on the Moodle the list of questions that I'm going to ask. Okay, so it means that a priori you should end up with 6. Okay, because you have the questions and you can prepare the answers. And we are here to help you preparing the answers. So do not hesitate to ask us. And I will be there. So, and perhaps it's also something that I would like to insist. I'm not only here to speak in front of you. Okay, I'm also here to teach you something. So it means that if you need my help, do not hesitate to ask me. Okay? And then some remarks. Yeah, some people complain about my slides, that the slides are not lecture notes. Okay, sorry, I have also lecture notes. So the slides are there to support what I'm going to say. Okay, so don't expect to have a list of bullets with long text that explain things, right? So you have the videos if you prepare. Each time I'm preparing my course, it means also when I'm traveling to Lausanne, okay, it's possible that I will make modification to slides or that I'm going to add a slide. Okay, so don't complain to this as well. We are in the 4.0 society, so I would prefer that you do not print the slides, but that you take the computer and follow the slides and take notes on the slides. It will be more effective. Yeah, do not hesitate to ask questions. This is also a principle that the students perhaps do not know, but you have to know that when you have a question, 90% of the people around you have the same question. Okay? So it means that if you have a question, ask. I'm here to answer. Okay? And what we are going to do is that we are going to solve a real case. Okay? So it means that I will also force you to take decisions. So it's not like a problem statement and a correction. Okay? So the problem is not solved. We have everything is well established to solve the problem, but the problem is not solved. You will be the owner of the solutions. So it means also that you will have difficulties to make some things converge, and it will not be just like I take the corrigé and I'm going to just follow what has to be done. Okay? You will have problems, and sometimes you will realize that the garbage in, garbage out is something that is real, and I want you to learn this. Okay, and don't hesitate also to discuss among yourself. Okay, so if you think something, confront your what you think with the others, and do not hesitate to criticize. Okay, it's very important that there is a freedom of asking questions here that you will not have in the future. It's much easier to say something which is silly in front of a professor, especially when it is not the exam, okay? Rather than saying the same thing in front of your boss. Okay? I'm not paying you. Okay? And my goal is that you learn something. So if you say something silly, I will explain you why it is silly. Okay? Your boss will not spend time for doing this. Okay, so take the opportunity. I'm the sparring partner. Okay, sparring? No, sparring partner. Sparring partner. Okay, so don't hesitate. I'm here for this as well. Okay, and then don't forget that what you write, what you present is what remains out of your work. Okay? This is true here, and this will be also true when you will be in the industry. Okay? You can be very smart if you do not communicate in a smart way, then nobody will see you as a smart person. Okay? Now, just a few words about the assistants. So they have prepared, they are spending time here in Lausanne, they have to commute from Sion, but they have also to do the PhD thesis or the research work. So it means that they are available, but do not overcharge them. So it means that if you have questions, so first ask among yourself and come with a structured question. So coming by saying it doesn't work is not useful for the assistant. Okay, but if you say I have tried this, I have written this problem in this way, I made those assumptions, and it seems that it does not work, then they have the skills to help you and the information to help you. Okay. Right. So at the end, I hope that we will have a lot of fun. Okay, and I would like that you take this in this way. So don't come here just to get credits, but to acquire knowledge, right? And all what you will learn here will be useful for your future, hopefully. Do you have questions? Try to speak loud.
So what kind of register are we used?
Yeah, okay. So in terms of the software that will be used, there will be several ones. Alessio and the other assistant have prepared, in fact, software that will be used. You will be offered a virtual machine. So it means that there is no need to install a lot of software on your computers. The only thing that you will need is a screen and an internet connection. Okay, and everything is prepared. Concerning the software that we are going to use, there will be one that is AMPL, that is Advanced Mathematical Programming Language, that is a software that allows you to state mixed integer linear programming problems. And you will also use another tool that is Belsim Valley, which is thermodynamic flowsheeting software that will be used for calculating flow sheets. And you will have sessions that will explain you how to use all the software. Other questions?
Today will be exercise.
Today, I will use the 10 remaining minutes to state the problem, and then you will have holiday in the afternoon. Okay, so it means that we will start officially the project next week. Okay, and the reason is that we are not sure that we have the complete list of students, and that we are going to we have to create very fast the groups so that we have an organization among us. Okay.
So the groups will be created by you, or
No, typically.
You can create.
So you can create the groups.
So there is a link in the module in which you can choose a group and assign it. Yeah. We need to understand which is the exact number of people of students in the course, because we have to adjust the number of groups accordingly. But still, you can choose your partner. And of course, if someone cannot find a group, we will have.
Okay. C'était la même question? Okay. Other questions?